what we were thinking to do is potentially utilize long-term temporal data following one patient over a long period of time from the screening results to predict the cancer trajectory or the future risk, and to utilize different sources of information, not only the images, but also the electronic health records or other data that we have of the patient. So, hello everyone. I just wanted to briefly talk about some of the work I've been doing with few shot segmentation and some of the future research I'll be doing for mammograms. So, I've had the pleasure of meeting some of you in person, but for those of you whom I've not met yet, my name is Suaiba and I'm from Bangladesh, and I completed my undergraduate and master's education at King's College London, and I focused mostly on biomedical engineering and AI for healthcare applications. So some work with fetal brain MRIs and with coronary MRIs as well. And as Inger mentioned, I formally started as a PhD student at the Visual Intelligence Center from January. And prior to that, I completed some research from April of last year focused on few shot segmentation. So, so why do we consider few shot segmentation, particularly for medical imaging? Well, training fully supervised models for medical images is quite impractical because we need large pixel level annotated datasets. They're expensive, they're time consuming, and they need considerable clinical expertise to get. And the alternative would be semi or weekly supervised schemes. They reduce the cost, but they're still dependent on large weekly annotated datasets. And once trained, these kind of models, they tend to not generalize well to unseen classes. So few shot learning is a promising way to address these challenges. And typically, as we will see, it is done in an episodic fashion, the training of the few shot models, where each of the episodes, they utilize a small sample of labeled images for training. That's known as the support set to then identify objects of the same class within the query set that we want to segment. And I wanted to start with just an overview of the implemented strategy. And the main idea was that we use an anomaly-based thresholding, and we use a self-guided module that outputs more than one prototype. We will go into this one bit at a time. So starting with how do we get these support and query images that we see. So the training, it involves self-supervision end-to-end in an episodic manner. So first we extract some random supervoxel from the 3D image volumes from the foreground class that then serves as a binary pseudo segmentation mask. And then from there, we sample two random 2D slices that contain that supervoxel class. And these two slices, they form the support and the query images. And then from those images, we feed them into an encoder. In this case, we used a ResNet 101 that generates the support and the query masks respectively. And once we have these masks, we want to get a prototype that's representative of that foreground class. And we do that using an operation called masked global average pooling that takes in this support from support features and the support mask. And then we get the original prototype, that is P. The operation is highlighted here. And then from there, we want to use the prototype to guide the segmentation of the query features. And the way we do that is by first calculating what is known as an anomaly score with a negative cosine similarity between the query features and the prototype. And then we apply a learned threshold parameter and a soft threshold with a shifted sigmoid that makes the process differentiable. And what we get out is a prediction for the query images. So this is what we're going to call the original prototype prediction. Okay, then we have the original prototype prediction, we have the original prototype and the support features, and we want to see how well this extracted prototype is at segmenting this support feature. So we feed it through this self-guided module, and then we sum up how much did we get correct, which is the true positive, and then the false negative pixels, and we compare with the set threshold. In this case, we just set a value of 1. So there are 4 cases. In the first case, both the true positive and the false negative are below this threshold. In that case, we resort back to the original prototype because that is the most informative. And in the case where only one of them is above that threshold, so if only the true positive is, we take the primary prototype, and if it's false negative, we get the auxiliary. And in the event that both of them exceed that threshold, we take a weighted sum, and the weights are just ratios of, for example, for W1, it is T, which is the true positive, over the sum of the true positive and the false negatives. Now, in this case, this is how we're choosing to combine them, but we could have alternatively gotten out both of these prototypes and then gotten 2 separate anomaly scores and combined them, or we could have chosen to get out 2 predictions and combine them. We could have used an average or maximum of these 2 instead of a weighted sum, but this is what seemed to perform the best. And I want to go into a few details about the inference phase and the loss and the evaluation. So the inference phase, we just use the labeled slices from the support volume and then segment the query volume slice by slice, 1 class at a time. And for evaluation, we used dice score and intersection over union. And initially, it was tested on the MSCMR dataset with the cardiac MR scans. And the loss that it was trained on, there were 3 primary terms. One was binary cross entropy, another one was this threshold minimalization term, and a prototype alignment loss term, where essentially the support and the query losses are reversed. And in this case, we started out with a single prototype, trained a model, and then used the pre-trained model as a baseline to train the model with the multiple prototypes. And we used the pre-trained threshold value to initialize our 2 new thresholds, one for the original and the other for the new prototype. The learning rate was initialized from the pre-trained one. And the other parameter that we empirically set was the minimum size of the supervoxels that we used. So in this case, the best solution was to use minimum size of 100 for our implementation and also the baseline. And for the total loss term, I chose to use the original and the new query cross entropy loss, the threshold 2 loss, and the prototype alignment loss, including both of the prototypes, the self-guided one and the original, but the threshold 1 loss was left out because this is what performed the best. And I want to talk about some of the results that we got that's averaged over 5 folds of that cardiac MR data. So it's for segmentation of 3 classes. One is the left ventricular myocardium, one for the blood pool, and then the right ventricle. And compared to the baseline model with a single prototype, the implementation using both different supervoxel sizes, minimum supervoxel sizes, seems to perform better on the blood pool and the right ventricle. But in the case of the myocardium, it doesn't quite do as well as the baseline, and it is the most challenging class, as we'll see in a bit. And the same trend was also seen for the intersection over union. And if we look at some visual results, I just wanted to highlight some results where from left to right, we have the prediction from a single prototype, the one with the combined prototype with the self-guidance, and this is just the 3 classes all together from the ground truth. And we see the white bit is the ground truth. The red one is the prediction, so where they overlap, it's kind of pink. And we tried to correct for over-segmentation, so the bits that are spilling out over the edges, that's red, we tried to correct for that. And this one, it's not super different, it's quite good. For the blood pool, for the right ventricle, we can see that there was some over-segmentation that we successfully corrected for, but it didn't quite get the whole structure. So, and the last one is the most challenging one. So we wanted to correct for where it over-segments, but it tends to over-correct in this case, and this is why the performance is not so good as the baseline. It just struggles with this one the most, but yeah. And the next thing that I was working on was applying the baseline model with the single prototype initially for the liver CT segmentation task, and I just had a few images similar to before. The white is the ground truth, and the overlaid red bit is the prediction. And it seems to pick up the liver successfully, but we haven't tested out on lesions yet. And we get dice score over a single fold of 0.7, but it needs to be investigated further to say something conclusively about this. And lastly, I wanted to talk about some of the future research directions. I'm considering working with breast cancer detection and mammograms, where breast cancer presents as masses, distortions, or microcalcifications in mammogram images. But what makes it challenging is that the tissue, the density of the breast tissue, it varies quite a lot. So when it's thicker, it's more challenging to detect and classify the masses. And usually the traditional methods, ML methods, they're limited to a particular type of density or a type of data set. And if we go to more complex methods, they do show some promising results, but there are still issues with data scarcity and computational costs. So what we were thinking to do is potentially utilize long-term temporal data following one patient over a long period of time from the screening results to predict the cancer trajectory or the future risk, and to utilize different sources of information, not only the images, but also the electronic health records or other data that we have of the patient. So some particular ways we were considering would be multitask graph CNNs, perhaps considering the data in a time series fashion. And we also want to use perhaps multimodal information bottleneck to pick out what are the most informative or relevant image pixels or tokens from medical text that can help us make a prediction. And potentially there is scope for few shot learning to be applied in the case of the limited annotated data set. So yeah, those are some things we're considering, and that is all I had to say. Thank you for your attention.